If not, we will leave set theory, and then we will start with metric space. Okay, we'll try to see distance between points. Okay, before we go into topology. Okay, where we discuss open set and closed set. So let's start with metric space. So metric space is meant to be a generalization of Rn. Okay, so you learn Rn in MA2. Right? So this is meant to be a generalization for Rn. So what's the definition of a metric space? So metric space is a set. Okay, it's a set. Okay, together with a function, distant function, we call it. So we write it as a double, okay, x comma d. And this distant function need to satisfy three property. So what's this function? What's the domain and codomain here? Okay, so the domain here is I give you 2 points in your set. You need to give me a real number. Tell me how far are they. Okay, so it need to satisfy three property here. So such that for all x, y, z in the point in the set, the following holds. So first, it satisfies a positivity property. So meaning given any 2 points, this distance should be greater or equal to 0. Okay. And when it achieves 0? It is only when s equals to y. Positivity. And symmetric. Okay, so you should expect symmetric. I go from KLIA to Xiamen University and going from Xiamen University to KLIA should be the same. Okay, assuming the road is the same. Okay, but now it's different now. Yeah, it's quite different actually. Whenever I go out from Xiamen, right, and then I come back, I feel like when I come back it's faster. Maybe it's a bit like when you go out, you need to like turn around and then you go out. But when you come back, it's just straight back. Yeah. So, but in metric space, we have dxy equals to dyx. Okay. And the lastly, most important property is this inequality, triangle inequality. Okay. In a lot of proof, we'll be using this property here. So dxy is less than equal to dxz plus dz. Okay, triangle inequality. Right. Okay, so example. Okay, for first example, instead of talking about R, right, we just straight away talk about Rn because R is when n equal to 1. Okay, so we just straight away talk about Rn if we want to talk about real vector spaces. Finite dimensional real vector spaces. So what's the distance in Rn? Typically, you would write, for example, the absolute value of x minus 1. But what is this really? Okay, what is this really? So you represent your vector as what? As some column vector. Right. Okay, say something like this. And y is this. Or how do you define the distance between these two vectors? Huh? Pythagoras theorem. Yes, by the Pythagoras theorem. So what's the Pythagoras theorem do? So you take the differences in each coordinate, okay, square it, and then you take the sum of them. And then you take the square root back again. Sometimes we call this a Euclidean norm, the Euclidean space, because Rn is a Euclidean space. Sorry, Euclidean metric in this case here. Okay. Can you check that the positivity holds here? Because you are squaring it, then you're taking square root back. And it is 0 when every coordinate should be the same. If and only. Yeah, I missed out one F. So very important here. If and only if. Okay, not just if. If is easy. If S equals to Y, then the distance should be 0. But if and only if. If it's distance 0, then the 2 points should coincide. How about symmetric? Symmetry on this formula. Can this number recognize x1 minus y1, y1 minus x1? Cannot recognize because you squared it already. And lastly, triangle inequality. Can you show it? How? How to show? Triangle inequality. How to show triangle inequality here? Can you split? How to split? So imagine you have x1 minus z1 plus z1 y1 square. So can you just split it? How to show triangle inequality? Any idea? Use the origin. Do you mean? Do you mean I use origin? How to use?
So
And
x1 minus y1
mhm,
and z1
y1.
z completely identical.
Yeah, sure. So, I mean, are you talking about like something like this? Like this? Something like that? But can you split this or not? Can you be sure that this is true? Even if this is true, right? How about after taking square root? I mean, you could try, but there's a more general property exists here. There's a more general property existing here. You know where this matrix come from? Pythagoras theorem. Sure, this come from Pythagoras theorem, but there's a more general property existing in this space actually. Got any guess? So I want to say that more generally, known space are known spaces are metric space. Okay, have you guys come across known space? Any norm, abstract known space. Inner space, inner space is about inner product space. So do you know which one you know? Known space or inner product space? Inner product space. Okay, then let's start from inner product space. So even more generally, inner product spaces are metric space. Okay, we will show triangle inequality from norm. Okay, so let's recall what are these spaces. Okay, I put out knots on inner product space, norm space, and metric space. It is the knot I written for the seminar I do with physics students. Last semester we have a quantum mechanics seminar, so I was introducing Hilbert space. Yeah. Talk about Hilbert space, you need to talk about completeness. But to talk about completeness, you need metric. Okay, so today we will run through this, quickly run through this connection. So how to go from inner product space to norm space, and then finally we go to metric space, which is the central subject for us for this week. Okay, so let's recall what's the inner product space is, right? So what's the inner product space? First of all, it is a vector space. So I won't recall what the vector space is. You can think of it as a 10 axiom it needs to satisfy, or you can regard it as a space that has a is a group is a group that has an extra group action by the field element. Okay, you can think of it like that. Okay, otherwise you think of it as a 10 axiom space. Okay, so you have a vector space. So inner product meaning there's inner product on this space. What's inner product here? It's actually a map. So this inner product here is another function. Okay, function again. So what function is this? So normally how we write this function here? So we will write as a angle bracket dot comma dot. Okay. So also taking two elements from my inner product space. So let's give this inner product space a name for V. Okay, so it's a function from V cross V to where? R. And we can do it more generally. We can go to C as well. Okay, we can go to C as well. Let's do it more generally. So we can go to C. Okay, so such that what? Okay, so there are similar properties need to be satisfied by this inner product. So such that for all P U V W say in V, okay, and for all scalar C here in this case. Okay. So what are the property you need to satisfy? So first we have these positive semi-definite, definite, and non-degeneracy. But what this word means, okay, I will write in a second. So if you take any 2 points, you try and input into your inner product, the number should be greater or equal to 0 as well, similar to what we have in metric space. Okay, right? Okay, with equality to 0, when this thing equal to 0. Okay, if and only if sorry, what am I writing here? So this one, I'm saying that this is a v dot v. Okay, v dot v. Yeah, v dot v. Okay, not any two, just v dot v. Okay, and then this number, when is it equal to 0? It is when v equals to 0. Okay. Yeah. No. So there's one example in your mind, right? You should think of it as the the what's that? What is v dot v? The example you met. Euclidean inner product, right? But v dot v will give you what? The length of the vector, right? Okay. Yeah. Okay. Second, there's a conjugate symmetry here because our codomain could be complex. So we will get, if you do v dot w, okay, you will get the conjugate of w dot v. So you cannot straight away swap it. When you swap it, there's the expenses of introducing the conjugate. Okay. Yeah. Okay. And the other thing is bilinearity. Okay. So bilinearity. Bilinearity. So what's the bilinearity here? So this word implies that it is linear in the second variable and anti-linear in the first variable. Okay, so what does this mean? So let me write down in equation. So if you do v plus w dot u, you will get v dot u plus w dot u. Okay. Or if you do kv dot w, you will get k bar vw. Okay, why is this happening here? Okay, why cannot just bilinear on both sides? Because there is a conjugate symmetry that control this conjugation. You can show that, yeah, you can show that by this conjugate symmetry and bilinearity, this should happen. Okay, but this is just a convention. You could set that it is linear in the first variable and then anti-linear in the second variable also can, but it is just a yeah, it's just convention. Okay, but the thing is, one of them must be anti-linear to satisfy this three property. Okay, if you want to have bilinearity and conjugate symmetry together. Okay. Yes, question. First one is which one? Oh, okay, yeah.
The inner product of V and V is
Always not real, just yes. Always real, yes. This is implied. Yes, that's right. That's right. Yeah, right. This one actually can be derived from conjugate symmetry. VV, the inner product of VV is equals to the conjugate of VV. So what's the number that equals to its conjugate? Is the real number. Yeah. Yes, that's right. That's right. Good. Because really this inner product is meant to imitate the length. Okay. Okay. So we have keep talking about length, right? So length in our case is this norm here. This norm is trying to define a length on the space, okay, on a vector space here. So what's a norm space? Okay, so norm space is similar, okay, but the function here, which we call the norm, this norm here we will write as a length function, okay, from, again, let's call this v, from v to r. Okay, from v to r. So the input here only one thing. You give me a vector, okay, I give you a number. So this norm here is what? Is a non-negative function in particular. Okay, non-negative function because we want our length to be positive. If it is non-zero, non-negative function. And such that, again, three properties. Okay, that for every v w in v, and some scalar. And scalar, should we fix it? Let's fix it around R. No, we don't fix like that. So we fix this as the field where this vector over. Should we set our field as C? Let's fix C then. So this is a vector space over C. Okay. Previously also over C then. Okay, so these are my scalar. So what are the properties we have here? 3 property as well. First, you still have a similar positive definiteness. Okay. This is definite and non-degeneracy. Okay, so what does this mean? This means if V is non-zero, then the length should be positive. Okay. So in other words, contrapositive of this statement is if your length is 0, it is the only zero vector data set. Okay. 2 is what we call the positive homogeneity. Okay. So what does this do? So this says that the length of a scalar multiple of your vector, okay, should be the norm of your scalar multiplied by the norm of your vector. So you can pull the scalar up by a factor of the norm of your vector. Right. So yeah. Okay. This property here is quite interesting, you know. If my k is a complex number, right? You know how complex number will react on your vector? What's the action of a complex number on your vector? You somehow rotate it. But you see, the result here is the length of the original vector is scaled by the length of that complex number. Okay? After rotation. Rotate or expand depend on the length of your rotation. Yeah. You might shear it. Is it shear? Is that the word shear? Shear is like you rotate and then you expand or decrease it, right? Shrink it, I mean. Okay. Okay. Third property, what do I have? Is the triangle inequality. Okay, triangle inequality here means what? The norm of V plus W is less than or equal to the norm of V plus the norm of W. Okay, so this is, you see, we are getting closer to metric space now. Okay, we have triangle inequality in norm space. Then metric space we know already, so let's don't write this out. All right, so my claim is the metric in Rn comes from an inner product. Okay, so I mean, how we go from these spaces here? How we go from these spaces? Let's say I have an inner product here, right? How I define the norm? How do I define the norm there? For example, norm of V. How do I define using inner product? Yes, I just do V dot V. Maybe we take a square root there. Okay. So you should check that whenever I give you this inner product, right, satisfy this property, you should check that the new norm I define here satisfy this 3 property here. Okay, this thing you need to check. And going from here, we could again define. Wow, long time no see, Pei Hong. We need to define the distance function from this, we can define a distance function from this norm here. How? I simply take the norm of x minus 1. So we can go from inner product all the way to matrix space. So you need to check out, you need to check. This is my claim. You need to check. Check at this definition, okay, that you carry all the property in norm, satisfy the 3 property that I gave you in matrix space. Okay. The claim is you can. It's not too hard. Actually, you just need to write it out. It's not too hard. Okay. But the hard thing is, I think, is here. You need to show that this inner product here will give you this triangle inequality. Going from non-space to matrix space is quite immediate. But how about going from inner space to non-space here? How do you prove inner product, triangle inequality in the non-space from inner product? Because inside inner product here, there's no, almost don't have inequality in this definition. So you need to derive. There's a famous inequality in the inner space. Cauchy-Schwarz inequality. That's the thing you need here. Okay. Cauchy-Schwarz inequality, what does this Cauchy-Schwarz do? Well, let us recall what's the Cauchy-Schwarz. Inequality. What does this Cauchy-Schwarz inequality do? Still remember, for any VW in V, what do you have? The U dot V, okay, V dot W in this case. So we use this angle bracket. The absolute value of this inner product is less than or equals to the length of V times the length of W. Okay, you need to prove this. Okay, you need to prove this exactly using the definition of this norm here. Okay, this is how norm relate to inner product. Okay. So from here, we can prove the triangle inequality. Okay, should we prove this? Let's prove this. So how to go from here to triangle inequality? So trying to prove triangle inequality in the norm. Okay, using the norm with norm. All right. So what can we do? Let's look at this V plus W, the norm of V plus W. What is this? By definition is what? Is the square root of inner product between V plus W and V plus W, right? Okay, but I think maybe this square a bit annoying. Let's square it. Okay. So what is this inner product here? How to calculate this? We need to use the bilinearity here. Okay, we use the bilinearity. So if I quickly compute it, I will get P dot V plus W dot W. In the middle, what do you get? V dot W plus W dot V, perhaps, right? But what is V dot W and W dot V? They are relation, right? Not the same. Same up to conjugation. Okay. So meaning what? If you add a complex number with X conjugation, what do you get? You get a real number. In particular, here you get what? Yes, double real part of V dot W, say. Yeah, right. Okay. So I mean, this thing is less than the norm of V squared plus the norm of W squared and what? 2 times the norm of V plus W. It's less than, right? less than or equal to, because you throw away the imaginary part, right? Or you might have a contribution from the imaginary part. But from Cauchy-Schwarz inequality, what do you get? This number here is less than the product of the norm of V and W. Right? Okay. And what is this? This is just norm of V plus norm of W squared. Okay. So if you square root on both sides, you will get the triangle inequality. Okay, so the triangle inequality is a result of Cauchy-Schwarz inequality. So now I prove to you that inner product space give you a norm space, and then you can check that the norm space actually give you the metric space. So the question is, this metric here come from what inner product? What inner product can you define on Rn such that you get this matrix? What's Euclidean inner product? What's Euclidean inner product? Yeah. So if I give you x dot y, what is x dot y here? x1, y1 plus s2, sorry, s1, y1, yes, s1, y1 plus s2, y2 plus s3, y3 plus dot, 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 plus s and y. So this is the dot product of R. Okay, and then this, so if you go through the process here, will give you the metric, the Pythagoras theorem way of Pythagoras way to calculate distance. Okay, so we'll say that this matrix is induced by inner product, because you can use this inner product to define this matrix. Okay, can or not? So I give you instead of I proving this specific metric Y is satisfied triangle inequality, I prove to you that whenever you have a inner product, okay, whenever you have a matrix that is induced by inner product, you will always satisfy the triangle inequality. And then the rest I didn't check for you. You can go back and check. It's quite straightforward. The other property, the other two properties. Okay. Yeah. Does it make sense? Make sense? Question? Question? First one. No, just say it's okay. You mean going backward? You mean is there an arrow going backward? What do you mean? Sure. Yeah, sure. Sure. There's no contradiction here, right? Metric space is a more general case. True, maybe there are metrics that's not coming from inner product. True, that's true. I didn't claim what you said just now. I didn't claim that metric space is small. I just say that if you are inner product space, you can make into a norm space, you can make into a metric space. This is not my point. My point is how to prove that Rn set the metric on Rn satisfied triangle inequality. This is my point. I haven't addressed that point yet. For that point, you just go and prove it. I mean, depend on cases lah, right? Depend on cases. If it is come from inner product space, then you use this method. If it is different set, and then I give you a metric, and if you cannot identify this thing is coming from inner product, then you need to use other method to prove it. Yeah. I didn't show you that everywhere you need to use this to prove out. No, this is not my point. My point is just to show that this Rn satisfied. This Euclidean metric on Rn is induced by inner product. And then I draw a broad conclusion that any inner product space is actually a metric space. Whenever you meet inner product space, you straight away get a metric space. This is my point. Okay. Yeah. Other cases, different way to prove it. Yeah. Make sense? Okay. Yeah. Okay. Okay, good. So we have talked about this. This is very important conclusion. This is exactly why we study metric space or this topology. So we are including quite a number of spaces that we can talk about. All right. What other example we have? So next example, maybe I won't go into details, but I want to give you an idea so that you can connect to different courses in this school. So next, I'll talk about an example in geometry, differential geometry. Okay. I think this course is open this semester, so I think it's every April for now at least. You could take it. So in the differential geometry of curve and surfaces, right? What they are interested in is called the smooth surfaces. As in R3, what does it mean by smooth? What does it mean by smooth? Meaning, sorry. Yeah, differentiable. But what is differentiable? So intuitively, you should think that there's no singularity. So there's no like weird thing happen. Like how to say weird thing, huh? If you think about differentiable function, right? Okay. I think first thing that you know about a function that's not differentiable is the function absolute value function. So you have a like cups like that. Okay. Sharp angle lah. Okay, you can understand a sharp angle for now. Okay. Sharp to the point that you cannot differentiate. So we don't want this thing happen on my surface. So it's smooth, no? Smooth, right? If got this, it's like durian, right? Not smooth. Okay, so we want a smooth one. Okay, so I don't want to go precise, but I just want to give you a broad idea for this example. So how do we define function here? Sorry, distance here. How do you define distance between 2 points? What we do here is we take the length of the shortest path. Okay, shortest path. Maybe we say curve in this case. Shortest curve. Okay, joining x and y. And this curve should lie inside the surface. Okay, so you see, there's a lot of word that I don't define well in here. So for example, what's the length of a curve? What do you mean by shorter curve? Okay, no, I don't want to define, but I want you to imagine. Okay, so this is just now what I talked about KLIN as a function. Let's say all these road doesn't exist. Go and find the shortest one. Go to KLIN, go straight to KLIN, and then come back. They should have the same distance. Okay, yeah. This is the point of this course here. Okay, the shortest curve there. Yeah. The surface is connected. Otherwise, I think we should define the distance to be infinity already. Yeah. Otherwise, we should define the distance to be infinity. You cannot go there with. Yeah. So to do this, need to be path connected for both of this. Otherwise, we define it to be infinity. Yeah. So this will define a distance. So if you go and take this course, you will check that this will define a metric. Okay. And how about let's give a few more examples. Let's give a real life example. Maybe not real life here. maybe in French. Okay, so this is what we call the French metro. Or actually, it's their post office system. So what's this post office system doing here? So you look at a set of point in R2, okay, such that their length is less than or equal to 1. Okay, so what is this? This is like a unit ball, unit sphere, okay, because it's R2. And define the following metric here. And let's define the following metric here. So I would say that the distance between these two is just taking the difference, okay? If this x point is a multiple of y, okay? I'll compute like that for some scalar y, so our scalar should be living in R. Otherwise, I just add out their length. Okay, can you imagine what this matrix is doing here? If it is on the line, scalar multiple, then I take their difference. If it is not, I add out their length. Okay? Can you imagine what this is doing? So to think about what this is doing, right, you should think about what's my set first. My set is a sphere, right? Contain this origin. Okay. So if it is on the line, okay, say something like this, on the same line, I just take their difference. So maybe I just compute the difference here. But if it is not the same line, what do? I add out the vector, the length of the vector. So what am I doing here? How to relate to post office? Relate or some metro system. So it's imagine that this origin is your center. Okay. So if you are sending a letter from here to here, so the distance is only here. But let's say you need to send a letter from here to here. What do? You come back to the center and then you go out again. Okay. So try and check that this actually satisfy the positivity symmetry or not? Quite symmetry, right? Very symmetry, I think. And triangle inequality. Okay. Yeah, try and check that. This metric satisfy the tree property. Okay. I think should be quite straightforward, but you just need to write it out. Got question or not? Okay, try check that. So exercise, check that this is this define a metric. Define a metric. All right, so let's us finish one more example and then we will take a break. Okay, so another example I want to introduce is some example in example. So fifth example, I want to talk about periodic matrix. Periodic matrix. So what is periodic matrix? I'm not sure any of you heard about periodic number. Okay, this is related to a periodic number. So let me introduce a metric and then I'll comment about how this relates to periodic number. So what is periodic metric here? So what's the set we are considering here? We are just considering the integer. Okay, we just consider integer. And how to define this metric here? So let P be a fixed prime. Okay, so P here refer to prime. So in maths, right, whenever you see P, almost it is prime. Okay, because prime start with P. So what can we how we define this metric here? So for any two integer x not equals to y, we can have x minus y equals to some integer. Okay. But by prime factorization theorem, right, you can factorize all the p out, okay, and the rest. Okay, uniquely, very uniquely. For some k in n, and for some n in z. Okay, where this n is no longer divisible by p. So we exhaust all the p factor up. And we can do this because we have the prime factorization theorem. Okay. And how do we define this metric here? It's quite interesting. Maybe there are a few equivalent way to do it, but we will do this. So if s not equals to y, okay, we can extract out k factor. And then we define this distance to be k plus 1 inverse. Okay. And then if s equals 0, meaning what? Equals 0. Actually, you can pull out as many p as you want, right? And then multiply by some by 0. So really, we just define this to be 0 because we want to satisfy the matrix property. So you see, what does this do? Yeah. If you have more factor get factor out, this number become what? Become smaller. Become smaller. So you could imagine if you have a large distance here, right? I mean, the usual distance, I mean, x minus y. The distance between two large number, I mean, the distance between two numbers that have a difference large becomes small, really small. So it's like inverting the normal norm using prime. Okay, makes sense? Makes sense? So at first they are very large, but after this periodic norm, the distance becomes small. Periodic metric, I mean. Does it make sense? I mean, how can you pull out a lot of p? You have to at least make sure this distance to be very big. Right? At least. Okay. So remember how you construct reals? How you construct real numbers? Sorry? Dedicate cut. Okay, I don't want that one. Another way. Which way? How you construct completeness of real? Dedicate cut, not very relatable here for the moment. What is relatable here? Distance of convergence. What kind of sequence is convergent? Cauchy. So how you form real numbers? You can take Cauchy sequence of rational numbers. Correct or not? How you include irrational number? Cauchy sequence of rational number that have limit in irrational. So here also the same. You consider convergence sequence inside this metric norm, and then you complete it. Fill in all the limits for the Cauchy sequence. Then you will get periodic number this way. Okay, so you start with Z, and then you fill in all the limit point for convergence sequence inside this metric. This metric will tell you what two things are within epsilon to each other, right? Okay, and then you fill in the limit. After you fill in all the limits, Z with the limits is called the periodic number, which we call the, so let me write here. So Cauchy completion of Z, we will get ZP, and the periodic integer. Okay or not? Okay, yeah. Cauchy completed. But I mean, maybe you in a different in different reference, right? They might have slightly different about the metric, but it's the same philosophy. Okay. If you want to check that this metric satisfies triangle inequality, actually it specifies a stronger inequality. So this would imply that dxy is actually less than or equals to the maximum of dsz, okay, and dzy. Okay, this is even stronger. It's less than or equal to one of them, no need to be the sum of them. Okay, you can check this. Okay or not so far? Is it okay so far? So far, okay. Any question before we take a break? There's actually one more example, but we will leave to next hour. Any question? Okay, so what I want to show you is this metric space actually permeates a lot of fields. You can find metric spaces in different fields. Okay. Geometry, number theory, and then what else? Yeah, so far it's like this. And of course, physics. Physics should take place in these spaces. Okay. Any question before we take a break? No. Okay. Let's break until 107. Resume 107.问一下 IT。怎么昨天没有睡？是我昨天有睡哦，也是睡不好，很惨。是啊，早上起来就睡不好，也是环境不好。没有看，感觉我以前在 LY 9月中奖，我觉得是学校不好，水不好这个区，我们要净化这个学校。Yeah. Yes, careful. Huh? How to do? Second part or meeting Bentar meeting. What time is it? 1. You can do this, huh? Bro. Or 2 in this. Sorry. 一个早，所以你也是深入包。If you not, then this question wrong already. So don't know. Okay, next thing to build this. To build up. 你也不会对啊，我有看过，有看到的。啥时候呢？反正是。That's 2 p.m. 然后 然后外面是 PM。Q 是一样，我知道，但是问题是 PM， 如果我是 PM 会懂 PM 跟 G， 我是 Q 很懂啊 ，Q 很懂，Q 是 Q 很 Q 太懂，对，分数太重。是，所以你可以 match 去 PM， 但是问题是还是回到一个问题，就是来这底层的东西，其他。Power cell 省学习，对，对 match 这样。Start 是一直的啥？哦，我知道你干什么。喂，对。power set 进到 C 的话是什么情况呢？ 这个话是来以后这种的，对对对，哦，把它变成decimal的，对，
有本地的信，对
对对，就那两边的事情。
为什么不产？
嗯，不是就是来，如果你有一堆
主要是你看加跟加还是有无穷个加起来的感觉。
无穷个可以看 sensor 流 number 来，
对啊，
那是一个 max sensor 流 number，然后 proof 但是为什么它完成化？它 max sensor 是这个东西 proof 很完全弄的，对。但是如果你有两个 decimal 一样的，
上看的跟什么上看那个抽象，看不懂
哪一个东西？
这个答案呢？
你哪一个
然后 P N 打去那个去打，他
打去001里面，
对他打去0.1，
对，打去0，
不懂他是怎么猜的。
哎，像他讲了，
他是先从 P N 打到0.1，他从 P N 打到 P N，我问为什么他从 P N 打到 P N？
要看他讲比赛，看他讲比赛，我不知道他讲比赛，所以我也不能够解释。所以你要懂他比赛，你才可以看一下你不然你听得懂他讲什么？
那可以
他讲什么？你有一个 set，我就是把它变成0点，他，哎，说对，就0点，对啊，对不对？
就是一个是啊，想象不出来啊！主要是
比如说嘛，你的 subset 是123吗？你要打去什么号码？0.123000000，
是数字就没有那个数字就那个。
哦，你打的是binary哈？哦，他打的是打出来的。有 order 不允许。哦，聪明，对，0到9，他10就打不出来，所以他讲把它变binary，就是第几个位，比如说123在的话，123位就给他放个1了。
那如果连续很多次的话，
怎么可以一出现很多次一个 set 里面？
就比如说有一个是1，有一个2，有一个是1、2、3这样子，
这是不同 set 是吗？
对，
不同 set，这样就不一样号码。啊，不是，这3个 set 对应的号码是0.1、0.11、0.111，不是？
对呀，
啊，
还是几？
对，但是我写嘛，check 哦，你就 check 哦，肯定是 well defined。你 check 它 implemented， but 一个重点 for 这个 decimal extension 就是你要 fix 一个 convention， 就是你的0.9999跟1.00000不可以同时存在。这个东西要 mention。你
拿多
0.999在这个 case 是0.1。对啊，但是会有问题，
不会有94，
对，会有对，但是不会来，不会的话，
就是我在的话0.0，
没有二进制只是 for 那个号码不了，其实但是你整个东西不是活在二进制里面，整个东西是活在 decimal， 就是10进制。我一开始也是以为我东西活在 decimal， 但是你整个东西其实是活在 decimal extension， 就是decimal extension 啊。但是你去 decide 那个1010的时候就是binary，然后你要 prove 这个东西是 invention。如果有2个这样的号码，它应该都要从2个一样的 set 来。
比如说2、3、4、5、6，后面全部都有，跟2个东西是不一样的，是一样的不一样。
你现在在讲吗？你现在有 set 啊？
是就 power set 嘛，就2后面的都有，就1没有2的，跟只有1的这个东西是一样还是不一样？对啊，下去
啊，这2个一样还是不一样？不一样啊，中国一样。
所以你要让他们去克服。
对呀，所以0.10000跟0.1是不一样的，因为我们在讨论说这2个号码是活在 decimal 里面，肯定不一样。或者是 binary 里面的话，这2个可能是一样的。 0.01跟0.100。binary 的话，这两个是一样。对，但是我们的那个活的地方是那个0到是一个 decimal 的啊。make sense。哎哎哎，我 define 的，是自己 define 的，自己 define。为什么要这样子哈？所以就很奇怪哦，很特别哦，就是他把两个很远的东西，透过这 metric 把它拉到很近哦，然后才会 define 出新的数字出来吗？才会 define 出新的数字吗？我们叫做 periodic number。我要 call 去 complete 里面的 conversion sequence。
它也是活在零
啊
跟一之间，
什么东西？
那个数字也是活在零跟一之间。expansion。
就现在，我不知道我可不可以把 periodic integer 写出来，因为我只 define 它 as a limit 罢了。我不知道哎，我没有真正在那边 work 过，把它 construction 是这样，可以 try and 写出来，但是写得出来。啊？呀，这是我们 define 的 periodic metric 啊。then 你要去 check 它 satisfy 那个三个 property positivity symmetric 和 triangle inequality。then 它就 define 个 metric 啊。写法本，名字吧，名字吧。
我不是 P
啊？
我们
什么意思
A1 有那个在 P。
你们学什么 ZP 啊？哦，不是那个哦，这个不是那个 mod PZ mod P，不是那个 Z mod PZ 啊，啊，这个是 periodic number。Yes。Sure。
是你的 prime factor 是你的那个 K 肯定。
啊，对，所以呢？
你一加 K over 的 inverse 一定是小于等于一，因为你 K 一定是整数嘛。
啊，对，所以又怎样？
跟的 distance of integer 是大于等于一，然后你的那一个东西是小，再加上他们两个都等于一。是吧？
没有问题啊，你的 distance 没有，这里
不一样的 define 方式而已。
不一样的 set，不一样的 set，在讨论两个 set，你的就是 OK 这样子。说这边有两个 set， 说一个是 Z with 平常的平常的那个so let me write this， 这是平常的，对不对？现在我们 consider 的是新的，可能叫它 DP 了，叫它 DP 好不好 ？DP 新的东西呀，它们不是同时存在啊。OK 了，啊，Yeah， 新的东西，哎，exactly，新的东西，我们在做新的东西，不是旧的东西，新的东西，exactly，新的东西，exactly，新的啊，Yeah，新的，exactly，so that's why 我们拿 call 去 complete 过后，我们会造出一个新的 space 出来，比如说 real line， 如果你放回你的 Euclidean metric call 去 complete 一下，还是他自己啊？还是他自己啊？因为他本身已经 complete 了，然后 yeah， 他的 limit 还是活在他自己里面。
这个是外面，
在外面
这个
啊，对，这个在外面。诶，yeah，你可以 prove 到那个 limit 不会在里面 ，and then 我可以 include 它进来，from 这个 periodic integer。 There's a few 有一个 field 在 study 这些东西啊 ，periodic number yeah。Hey, hello. Let's take attendance. 周一分。Okay, 周一分 yes. 千西苑okay. Lee Pet Hong here. Brian here. Leong Yen late à, Leong Yen. Okay. Gary, 建祥, Jing Jie, 思雨, Jimbo, 丁宇, Ziqian, Sai Ye. Jia not here. Yi Heng, Yang Ke not here. Wen Chuan. Hey, who are you behind? So what's your name? You attend the class first time today. So what's your name? Cheng Hao Ming. Can you spell for me? Okay. HAO MIN. Connected or not, the last two words? Three word. Three. Okay. What's your student ID? MAT204. 144. Okay, I will add you into the Moodle. And then actually they already do one assignment. So maybe we can discuss when you can submit. Yeah, maybe we can discuss. You send me an email, say that you are a newcomer, and then we can sort it out. Sorry? Yeah. So you are registered. You register, you confirm. You pay for the course already. Okay, because they don't include you in the system yet. Sure. Okay. Yeah, send me an email, and we will sort it out. Okay, so let's continue with an example of metric space. So we have discussed one matrix on Rn, right? So we can define few more other norms, okay, on Rn. Maybe you have actually seen them in different courses, maybe PD or what. And the functional analysis actually will play more norms on Rn. So just now I said that norm can define metrics, right? So I can just tell you what norm I put on it. What is the P norm or P matrix? Usually we say P norm, seldom we say P metric. So what's this P norm here? So instead of taking square and square root, right, we can take power of P for any real number. Okay, so we can do this. So if you give me a vector, okay, because difference of two vectors is still a vector, right? So I just tell you how to compute norm for this vector. So how do I compute it? I take the P power of every component, add them out, and then take the P fruit. And this is what we call a P norm. So when P is 1, what happens? This is the usual one. Distance in R, right? If it is square, then it's the Euclidean metric. Okay, and another norm is what we call the sup norm. Okay, supremum. So we will write as infinity here. This is a norm that's at infinity. So how is the sup norm here? It is taking the maximum, okay, of one of the coordinate. The maximum of them. And then absolute value of each coordinate, and then I have maximum of them. Okay, later we will see how does this affect the ball inside these spaces. Okay, so now I define it. Okay, you need to prove it. Prove that these are the metrics. Very good exercise. There are a few exercises to check already. And what else? we don't stop just with these elements, right? We can start with we can have example on function, set of function. Okay. So in particular, set of continuous real valuing function. So this is the subject in calculus. Yeah, in calculus 1 and 2. That's real valued functions defined on the interval, closed interval AB. Okay. So what kind of norm we can define here? We can define a sup norm as well. There's a sup norm as well. It is quite similar to what we have defined just now. So it's taking the sup of the length of f. So what's the length of f here? We can't really measure the length of f, but what we can measure is the length of fx, because fx is the thing that is real. Okay, so we can take supremum of this guy. So meaning we look at the image. We look at the image of the function, and then the image of the function live in real because it's a real value, and then we take maximum supremum of it. We cannot take maximum because you know the problem, right? If the maximum is not in there, then if the sup is in this set, we will call it a maximum. If it's not, the sup will lie. The least upper bound might lie outside the set. Okay. Okay. What else? What else? And we can do L1 norm, for example. So what is L1 norm here? So L1 norm is just the integration from A to B of the absolute value of f. Okay, we want to make sure there's no negativity coming out here. So I take absolute of f. And we also can define L2 norm here. Okay, L2 norm. Maybe you took some courses that say that some function is square integrable, then meaning this norm is finite. Okay, if a function is square integrable, yeah. You need to take absolute value. Here, inside here. Should we take that? You already squared it out.
It's a function.
So, no, wait. No. I mean, this f squared means you square pointwise. So should be fine, right? Positive. Be fine, right? LP lah, but here is square already. P because P might not be even, so you might have some negativity coming out, but square definitely no negativity. Of course, if you define for LP, but LP if it is not square, then there might be still negativity, so you need to put absolute. But F square, even if you put absolute, it's still the same. Does that make sense? Make sense? Okay. Yeah, you can try and define LP norm, okay, for function. Similarly. So what's the LP norm? Can define it. Okay, so you can see that these are all metric spaces. So the member of a general metric spaces we often call points, although sometimes they are function, right? Like in this case, they are function, or sometimes it's just point in Rn. Okay. Sometimes maybe it could be a set. Okay, set. Yeah. So in general, we just call points. So that's why this course is called a point set topology. Okay. Everything we regard as a set, and then the member of a set are just points. Okay. Although there might be function, set, so on. Okay. And so now we're gonna define ball. Okay. Definition. Let XD be a metric space. So the open ball of radius r greater than 0, okay, centered at x, okay, is defined by the following. So you should think that this is after I define matrix, right? So I need to use matrix here. So how do I define the ball here? So if it's centered than x, it is all the point that is distance r away from y, from x. Okay, centered than x. All the point that is distance r away from x. All right. So can we do a little exercise here? Let's do a little exercise here. So let me see. A moment. So what kind of okay. So let me write down some notation here. Let me keep some notation here. So let's okay. So let's copy this guy down. And let me paste here. Okay, I want you to draw a picture. Okay, let's draw a picture. Do an exercise. Okay, draw a ball of radius. Let's say what's the radius we want to pick here? Radius 1. Okay, let's draw a ball of radius 1 in R2. Okay, R2 with, let's say, the 2 norm, which is the Euclidean norm. And what? And how about 1 norm? Okay, 1 norm and sub norm. Okay, so we call the L infinity. Okay, try draw this picture. How this ball looks like. And I give you maybe until 1:30, discuss with your friend. Draw 3 pictures. A ball of radius 1 in these 3 norms here. Okay. Does it make sense? You know what my question is? With different distance, draw what's the ball looks like in R2. R2 can draw, right? It's just a flat surface. Try and draw. Discuss with your friend. At least one you must know how to do. At least one you must know how to do, right? Which one you know how to do? You know, I mean, when P equals to 2, right? P know you know how to do. It's good. I mean, when P equals to 2, what is that? What is it? Yeah. What's the ball looks like? Circle, right? Yes, correct. So how about the other? Draw it. Go and draw it. Get the equation now and then draw what point satisfy the equation. Quick. Okay. Try and verify. Just now we said that when it is 2 norm, it's just the unique circle. Verify it. Why is it a unique circle? And then for the rest, write down the equation, draw the picture. Okay. Yeah. I give you until 1:30. Discuss with your friend. And I think my calculus 2 student will be very reminiscing of this example here. Try and draw it. Yeah, try and draw. Go down. Oh, see the definition, huh? Okay, let me besides this, and then I think we can show this here. I just, the L. Oh, you mean this L infinity, huh? Oh, this is the name for this guy. So let me go like this. Okay, one better. Okay, yeah, work it out. So our n is just 2, right? So you need to stop at 2 here. Stop at 2. Okay, and then work it out. So how to go from norm to distance? You just replace the thing inside here to be s minus 1. Oh, ball of radius 1. I forgot to tell you one thing, right? What's the center of this ball here? Let's pick another center. Let's pick 1, 2. Pick 1, 2. Okay. Because last time we said sphere must have 2 properties, center and radius. Otherwise, you simply find the ball. So let's find 1 and 1, 2. But should be the same. If you just shift the center. Okay. Yeah, discuss with your neighbor. Discuss with your neighbor. Discuss with your neighbor.
I just like signal.
Infinity norm. I never see that notation. Because why? No, I never see that notation. Usually they say so. Yeah. We can take maximum here because there are infinitely many in here. So I can take it. Okay. Try and draw. First, you need to get the equation first, and then try and draw it out. First, take the equation first. So maybe I give some hint, see if you get the right equation or not. So let's say I got 1, 2, 3, 1, 2, 3. So first is the Euclidean one. So the 2 norm. Let's say the 2 norm. What's 2 norm here? What's the equation you need to satisfy here? X1 minus 1 squared plus S2 minus 2 squared equals to 1. How about the 1 norm here? The absolute value of x1 minus 1 plus x2 minus 2 is equal to 1. Okay. Not equal to 1, but less than 1. Less than. Because we're talking about the ball. How about the subnorm? It is the maximum of either absolute value of x1 minus 1 or absolute value of x2 minus 2. Equal. So what point satisfies this equation? What point satisfies this equation? What point satisfies this equation? Okay. So let's move further. How about we move this? I think this is a bit harder. So move it down. Okay. Anyone get any meaningful picture or not? Do you see other picture, other shape other than the sphere, other than a circle? Square. Okay. Other than square, no more. Okay, let's see which one is square, which one is circle. Okay, first of all, does everyone agree that in 2 norm we have this inequality here? Agree? Okay. So what is this? When this is equal, right, this is exactly the unit circle. Okay, so if it is less than 1, you take everything inside the unit circle here. So let me quickly plot this. I think this one, everyone quite happy about this. For 1, 2. Unit 1. So you'll be touching here, and then here. So inside here. Okay, sketch, just a sketch, not very round. Apologize for that. How about sub norm? Sorry, less than, right? Less than. Which one? Sub norm, oh, less than, right? Less than, should be less than as well. Less than as well. Thank you. Okay, so what point satisfy this? And what kind of x1 will satisfy this? What kind of s2 will satisfy this? Sorry? Open rectangle. Okay, so how do you check it? How do you check it? How do you check it? Maybe you can see where this equality happens, right? Okay, where this equality happens, either one of them reach 1 and then the other don't reach 1, right? So let's say x1 minus 1 need to reach 1. What happened? S1 could be 0 or 2. Yes, 0 or 2. Okay. And how about S2? It could be 3 or 1. Okay, 3 or 1. So let us plot this out. So where's the center here? Center is 1 with 2, let's say here. Okay, is it a bit too high? So let me move it down a bit. So 2 here. 0 and 2. And x1 can go from 0 to 1 to 2. So go from here. So let me use maybe here, 0 to 2 here. Right. And then S2 can go from 1 to 2. So let me use another color. Here to here. Okay. So now how we decide this? It could be everything here to here. And then everything from here to here. Okay. So if this is equal, so this is like the boundary, correct? Okay. So this boundary will satisfy maximum equals to 1. Okay. But we want something less than 1. Okay, strictly less than 1. You can verify that. I think should be the thing inside here. Make sense? Does it make sense or not? If you are a bit away from this boundary, you are closer to the center. So you cannot achieve 1. So you achieve something less than. Sorry?
When you got this combined by
Yeah, sure. Yeah. Because maximum can be achieved by either one of them. Yeah. Okay, so this is a square. Okay, so this is a square. Yeah, under sub norm, this ball look like a square. Okay, so we don't want to include the boundary, so let's remove the boundary. Maybe remove like this. Don't touch the boundary. Okay, like this. So it's a square. Under sup norm, this ball becomes a square. Okay, how about this? The last one. One norm here. Similarly, we can check the boundary as well. Check from the boundary. When does this expression equals to 1? The left expression. Okay. What are the points in the boundary here? 0, 2 is in the boundary. 1, 1 is at the boundary. Okay, when it is equal to 1. When I say boundary here, meaning when this equation equals to 1, yeah, I haven't defined boundary for you. So how about 2, 2? How about 1, 3? Okay, so to see this general pattern, right, you should really look at the basic case. So what's the basic case here? Actually, what is the point that satisfies absolute x plus absolute y equals to 1? What's this shape here? Meaning I shift it to the origin, right? I shift it to the origin. So what's this case here? What are the points that satisfy this? These are what? These are what? You can get x equals to 1 minus y, x equals to 1 plus y, and then maybe minus x equals to 1 minus y, minus x equals to 1 plus y. So these are the 4 lines, right? The 4, I would say, these are the boundary line, but how to describe this line? So these are the linear graph, right? Linear graph. So shifted y equal to x. This is what I'm going to say. Shifted y equal to x, and then the reflection of y equal to x. Fair enough. Does it make sense? Make sense or not? Make sense or not? Make sense? So what I want to say is these 4 lines made out this boundary here. Okay. Okay. And then to get this ball is exactly everything inside again. So if you move closer to the center, you won't achieve the equal sign. Okay, because you are closer to something that you deduct. Does that make sense? Make sense or not? Okay. So you can see that this is maybe a shifted rectangle. It's like a kite. It's a kite. Sorry. Still a square. Square. I think square is a square. Yeah, just that my sketch is not symmetric. Sorry about that. It's a square, I think. Yeah. No way.
Like if you like the x coefficient.
No. No. I just shift it only.
Yeah, if like
If what?
if the x coefficient become 2 or 3.
You mean 2 times, right?
Yeah.
2 times. That's definitely that's the linear algebra. Yeah, you do a shear. Yeah, you do a shear to the coordinates. But yeah. Yeah, when I say rectangle, rectangle include square, by the way. Rectangle includes square. Okay or not? You guys remember this example? Don't remember? The assignment one. Bound the ball by a square, square bound the ball. Forget already. Calculus 2. I made them prove some result in calculus 2 related to topology. Later we will make this statement precise. Go back and look back your calculus 2 assignment. Yeah. In assignment? Assignment. Yeah. I can show you next time. Okay, later we will make that as an example, that connection precise. For now, what we do is we look at ball in different norm. Even in the same space, with different metric, you are looking at different ball already. Okay, but in general, we just call them ball. Okay, open ball. All right. What time is it? Okay, keep going. Let's go on. So Yeah, so next we'll define neighborhood. Okay, what do we call the thing a neighborhood? So who regard as your neighbor? Who can you regard as a neighbor? So start with a metric space again. We want to measure distance. The subset, okay, y in X is a neighborhood of an element X if there exists a radius such that, okay, such that there's a ball of R around X, okay, lie inside Y. Okay. So this is quite intuitive, right? So for example, you stay in Taman what? You stay in Taman what? Simple. Okay, maybe Taman Sansurian. Why you say that Taman Sansurian is your neighborhood? Because you got a house there. The house contains you. Make sense or not? Does it make sense? So when you say Y is a neighborhood of some point, because you got a ball that contains you inside the set. Right? Does it make sense? Okay. So Taman Sansurian is your whole neighborhood because you got a house there that contains you. Make sense? Huh? Okay, so this is neighborhood. Next, bounded. Okay, what about bounded? When to say a subset is bounded? Okay. Sometimes let me jump back a little bit. So let me back up a little bit. So sometimes I will write notation, maybe my radius put at the top and then the center put at the bottom. Okay, sometimes you see this. So don't confuse. A subset X of a metric space is bounded if S is a subset of some open ball. Okay. So you are bounded if there's some open ball that bounds you. Okay. Make sense or not? There's a ball that bounds you, then you are bounded. The subset is bounded. Okay. If you are unbounded, then there's no house that you can stay. Right? Because you're unbounded, you're too tall already. Okay. All right. So proposition. Proposition. If S is a bounded subset of a metric space X, then for every point in X, there exists a row greater than 0 such that S is a subset of ball with radius row that center at Y. That center at Y. Okay. Can you think for a moment what this says? So if you are bounded subset of X means what? There's a ball that bounds you with some center point. Okay. So I mean, this statement, right, is really very geometric, not geometric, but topology, because we cannot draw the real square or circle for most of the case. So let's draw it like this. So let's say this is your X. Okay. Inside your X, you have some set. Let's say S, bounded one. So what does bounded mean? Bounded just means that there's some ball. Okay. You should imagine that this ball might not be circle. Just now I already show you the square ball. So there's a ball with radius R, maybe centered at somewhere here. S, that bound S. Then what? Then it says that for every point, no matter where my points stay in metric space, you can build a ball that can eat S again. That contain X. Can you do that or not? Can you think of a way to do that? Maybe I give you more room, give you bigger room to imagine. So I take any point in the space X. Can I build a circle, a ball that contain X again? Sorry? Contain X.
The ball is inside the screen X.
The ball is inside the X. Of course not outside because I don't have space to draw. So I mean okay. Let me make it bigger. Yes, of course you don't want to take something outside the set S. Wait, let me. Yeah, of course you don't want to go outside. Okay, yeah. Okay. I mean this X is everything, literally everything. So yeah. Okay. So how can we do this? How can we do this? Yeah. How can we find? So let me fix the Y. Let's say our Y is here. How do you find the row that contains? How do you build? How do you build the radius? Radius here. Distance from X. So you mean from 0? So in your mind, there's an origin there, is it? So should you? Okay, let us think about origin somewhere here, maybe if you like. But maybe we don't need this origin also. Any idea? What time is it? I think I don't have much time. Maybe we can revisit this, but any idea what row you want to pick? There is some estimation here, but how you include the estimation? How do you build home around Y that includes this guy? Huh? So my claim is, you want to try? You guys want to try? Huh?
The ball must be in X.
Sure. The ball actually, the X is unbounded actually, so don't care about my boundary. This is actually not unbounded. I just so that's why just now I said not very important this. Okay, I draw like this, to differentiate the not important. Yeah, extend what as long as you want. Okay, so how to find this radius? Even if I have boundary, you should also can find one, Yes. Okay. Okay, I mean that ball maybe is a chap ball. I mean, how to say chap ball? It's not a symmetry. You need to throw away something that's not in X. But anyway, that one I need to then in that case we need to change the definition a bit. But anyhow, let's say this boundary is no boundary for X, okay? So it's infinite. So how do you build this ball here? By using this distance here. Sorry? And then, is it enough or not? Distance of S and Y is where? You see, distance of S and Y is just maybe here. Can you include everything in X or not? Plus R, correct. So go back and try and show this ball will include your S using a triangle inequality. Okay, build this ball around Y. Then this ball will contain X. Use triangle inequality. So you need to take the distance and then you include the R. Okay, yeah. Make sense? Okay, I'll go ahead and try, and then we will resume this example next class tomorrow. What is R here? What is R here? What is R? R is this radius for my ball here. Okay, this R is the R that I draw in this picture. So this is the given by the boundedness of S. This is given. Bounded, then there's yeah. So this this R is given by the bounded property. Long Yun and Gary will have meetings there. Okay.
Yeah.